Hello everyone, I hope you all are doing well. This is the first video of EMT lecture series, and this video focuses on the prerequisite knowledge that you people should have in order to seamlessly dive into the world of EMT. Alright, so the first video will focus vectors. We will be introduced to vectors, what they are, and some of the algebra related to them, because it will help us in future for solving the problems related. So yeah, that's important, and so I highly recommend you people to watch that video and all other videos, prerequisite videos, in which we will be introduced to coordinate transformation and about del operators, what their expressions are. These are the helping materials, and please watch these videos, and at least you should have a knowledge about them, because mostly we directly jump into the main drama, but we should know these linking things. Okay, they help it to make the experience better. Okay, so yeah, let's start it. First of all, we should be introduced to what vectors are. So vectors are actually the physical quantities have we have defined in physics, the physical quantities, and these physical quantities are the measure of something. Okay, we define those quantities. Vectors are actually the physical quantities, are a type of physical quantities. We know about scalars and vectors from a very start. Scalars are those physical quantities which only require magnitude for their complete description. For example, if we were asked that what is the temperature nowadays, so we'll say it's like 37 degree, for example. This is the average temperature nowadays. So now, to describe the temperature, you do not need to identify the direction you are talking about. Okay, you are not saying that it's 37 degree in the x direction and it's 7 degree in y direction, and this is z in z direction, it's different. No, that doesn't matter. Okay, so you do not need to specify the direction you are talking about when you are talking about temperature. Okay, so you need to know only the magnitude, not the direction. Okay, there is a fact that temperature is a point function, that it could be different at different points, but it's not a directional quantity. Okay, it doesn't require direction. Now let's talk about vectors, it will make it even better. Okay, for example, there is a person here who came to you. Okay, this is that person and this is you, and this person asked you to tell him that where is AHC mall, shopping mall. Okay, we love shopping. So he asks you where is AHC mall. So what you will do, that you say that you have to travel a distance of 365 meters to reach AHC mall. So I would ask you people that would that description, that numerical description, magnitude only, suffices to describe that person the location of AHC mall? No, because he can either travel 365 miles straight away, okay, or like that, or like that, or like that, or like that. Okay, and there are only few of the paths that are 365 miles, for example, or meters, and they will reach that location, not all of them. Okay, so for the complete description of a location of some point, okay, let's say it's AHC mall, this is, we want to describe the location of AHC mall, then what is needed, we need to describe the direction as well as the magnitude. Okay, for example, what you will say is to travel 20 meter in x direction. Okay, from this point he is standing, you have to define the starting point as well, which will be like taken as origin. For example, 20 miles ahead, then you have to travel the rest of the miles, which could be, you can calculate it, maybe it's 345 meters you have to travel in y direction, for example, and you'll reach AHC mall, or for example, or there could be other paths as well. It depends which path which roads are there, and and all that stuff. So you are understanding my point, right? To describe the location of something, you have to tell them the magnitude as well as direction. Telling them only the magnitude is, worthless. That's a worthless information, because it doesn't completely describe or gives the it doesn't completely gives the information you are looking for. So this is how we felt the need of vectors, because there are some quantities, there are some things that requires both of these things for the complete description. For example, location, or we can say the position of something, position vector. That is how we know about position vectors. Position vectors are really important. So we have position vectors here, and we represent position vectors by r symbol. Okay, and they are given by x, which shows the distance or magnitude of distance in x direction, that how many units of meter, how many meters or units we have to travel in x direction, multiplied by the I hat vector, which shows that it's x direction. Okay, these are unit vectors. Unit vectors shows the direction of the vector. So plus y into j hat, what units we have to travel, y units we have to travel in j direction, and z units we have to travel in k hat direction to reach a point. For example, this is the point P whose location we are showing. So this is the vector, this is R vector, and it is origin. Okay, and yeah, let us draw it in 3D. So if you draw it in 3D, then it will look like that. This is the P point, and here we are. This is the R vector. Position vectors are really important. So this is y, this is x-axis, and this is the z-axis. Mostly this convention is taken, and this is a projection on, this is, these two forms the xy plane. Okay, and the point P's projection on xy plane is here. Okay, and if you draw a vector starting from origin to this point, let's say, you can call it as a row vector, for example. And if you want to find its, x units and y units, what you will do is to make a perpendicular from this point on x-axis, so it shows the x units you have to travel in x direction. Okay, then you'll draw the projection of this point on y direction. This gives you the y coordinate of point P, and z coordinate is simply, you can see this whole length is the z coordinate. And if you want to see it here as well, you can put the projection on the z-axis of P vector. So this is the z coordinate. Okay, only few people manage to understand these 3D figures. Okay, I hope you people understood it, and it will be made more clear when we will be talking about coordinate transformations or maybe coordinate systems. Okay, we will talk about Cartesian coordinate system in one video, then we'll talk about cylindrical coordinate system, and then we'll talk about spherical coordinate system, all of them in separate videos, and you can watch your desired video. So this is how these are written, and yeah, this is the angle that this r vector makes with z-axis is gamma angle. Okay, the angle that this p vector makes with the y direction is beta angle, and the angle that p makes with the x-axis is alpha angle in general. Okay, we just name it. So yeah, this is how the position vector r is written, and these figures are really common in EMT problems when you are finding, for example, electric field intensity at a point P due to a line charge, due to a point charge, due to a sheet of charge, or something like that. Okay, these figures are really common, and you'll see them multiple times while solving the problems or in description of something. Okay, in dipoles, for example. So this is a really common figure, and you should be familiar with that, and try to get comfortable with tough things. Okay, because avoiding them doesn't reduce the problem, it will elongate it until you have the courage to face it. So be comfortable with tough things because they are not tough. You just have to give some extra calories to them. They are not that much tough, and this is something that I make myself reminded of as well, because sometimes I also tend to avoid things thinking that they are difficult and I will never be able to understand them, but I manage to understand them if I just get exposure to that thing again and again, and I'm just truly trying to grasp it, so it becomes possible. Everything is possible in this world, even everything. You just need to have enough courage to make yourself convinced about facing it. So this is how we were introduced to position vector. This is the first vector that I told you people. So you know now what vectors are. Vectors are those physical quantities that requires magnitude as well as direction for their complete description. For example, position vector. For example, position vector, if to locate the position of a certain object or a point, you need to know the magnitude as well as the directions to reach that point. Okay, so as we now know what vectors are, we now need to know how to write them. What are the symbols we use, how to denote them. As we now know what vectors are, now we need to know, as we now know what vectors are, we should know how to denote them. For example, when we write them on paper, how to distinguish between a scalar quantity and a vector quantity. So uh, normally what happens is, not normally, it's the rule that is followed every time in case of vectors and scalars. So you denote a scalar by a simple sign. Okay, there is no rule for scalars. You can denote them by any symbol, but for vectors you have to be specific. Okay, so in books it's easy to use bold letters. That is why in books you will see a vector quantity which is denoted by an alphabet, for example, which is in bold character. Okay, for example, let me see any vector quantity here. Wait, this is moving multiple pages, but I'm not getting even a single vector. Let me get some other book. Letters which shows vectors. What we use when we are writing, for example, just as I'm writing, I can't bold it again and again and again. Okay, what I'll do is use this thing. Okay, a with a arrow over its head. Okay, this is the b vector, c vector. Sometimes books also follow it, but they both are correct. But if you are writing yourself with hand, okay, what you will do is put a arrow over the unbold character. Okay, this is b. Okay, this is how we denote vectors. Now for example, this is a vector A. Since we know it requires magnitude as well as direction for its complete meaning, so what we write it mathematically is we write a vector that is equals to its magnitude, which is A, simply unbold, and it shows the magnitude of vector A, multiplied by its direction, and the direction is given by unit vector. Okay, so this is the A with a hat over it shows it is a unit vector of vector A. Okay, this shows the direction, this shows the magnitude. So magnitude as well as direction for its complete description. So that is how we write it. Now, how to know the magnitude of a vector? For example, let's say we have a vector whose x component is ax, I hat, y component is ay, j hat, z component is az, k hat. Now they can be numbered 3 to 5, they can be variables or anything. Okay, I'm just writing it in general. So if I want to find out its magnitude, that is represented by a, or you can represent magnitude by this notation as well. Okay, these are modes, okay, with a vector sign which shows the magnitude of vector A. Both of them shows or denotes the magnitude of vector A, that is given by under root of ax square, x component of vector squared, plus y component of vector squared, plus z component of vector squared. Okay, this gives the magnitude of vector. Now what about the unit vector? You can find out the unit vector by dividing the vector itself by its magnitude. Okay, you will find it if you are given a vector. For example, you are given with this vector 3i hat plus 4j hat. What you need to find out is its magnitude and direction. So for magnitude, what you will do is 3 squared plus 4 squared, because z is 0, so z squared doesn't matter. So this gives you the magnitude, which is 5. Now you want to find out the unit vector, and for unit vector what you will do is to divide this original vector by the scalar quantity, which is actually the magnitude of the vector. Okay, so you will get the unit vector of vector A. This is the unit vector. It shows the direction of the vector and its magnitude is equals to 1. Okay, because it shouldn't contain any value, that is why its magnitude is 1, and it just contains the information about the direction of the vector. And this is how you calculate unit vector, its magnitude and all that stuff. You should know about it. Okay, now let's talk about some other stuff. Position vector is one of the example, and you can write like this is the position vector, and in Cartesian coordinate system you describe the position vector this way. In other coordinate systems the description is different, the parameters are different, the directions are different. So this is how you describe the direction in Cartesian coordinate system. Now let's talk about addition of vectors, how you add vectors. Okay, because if you are given, for example, r vector, okay, and you have to add with 3r, how you will do that? Okay, how this works? This is really simple. Okay, like directions will be added into each other, unlike directions will not be added to each other, they will be written like that. Okay, for example, you can't add x I hat with y j hat, because I hat is a different direction, j hat is a different direction. These are three basic directions. They cannot be added to each other. For example, you know this thing, algebra thing, that x plus 3y, you cannot solve it further, it's the end point. But if you are having this situation, x plus 2y plus 3y, okay, you can add similar variables into each other. For example, it's 5y resultantly, but they cannot be further added to each other to form a single result. Okay, this is the final point. That's how I'm telling you that, for example, if you have if you are adding vectors, then I hat directions will be added to each other, j hat will be added to each other, k hat will be added to each other, but they cannot be interchangeably added to each other to form a single result. Okay, they remain separate. Okay, because they are independent of each other. and they cannot be added to each other. This is a property that you have to follow. Similarly in subtraction as well. Okay, so for example, if we have r vector, we know r vector is equals to xi hat plus yj hat plus zk hat, and then we have 3r vectors, so we have 3 into xi hat plus yj hat plus zk hat. Then what will happen is 3 is a scalar quantity and it simply multiplies with all of these. So it's 3 into x I hat plus 3 into y, because 3 multiplies with all of the quantities inside the bracket. So this is what we are left with. How to simplify it further? So I hat things will be added into I hat things. So we have these two only I hat stuff, so numbers, and we will add them into each other. This is 3x and this is x as well, same variable as well as same unit vectors. Okay, that variable thing matters as well. If you have 3y I hat plus 3x I hat, then though they have similar unit vectors, but they cannot be added into each other further on to give a single result because their variables are different now. Okay, so don't forget the basics. They always exist and there are no exceptional cases. So x I hat plus 3x, it makes 4x I hat. Similarly 4y j hat, similarly 4z k hat, and this is the final result. Okay, what else you can do is to take 4 as common, and you have 4x I hat plus y j hat plus z k hat, and since this is r vector again, so you can write it as r vector. You can do it even here, but I just wanted to elaborate some points, that is why I expanded it. Sometimes there is a 10 marks question that has only steps to do, so you elongate it to make it worth 10 marks, because we normally think intentionally that the greater the marks of a question, the longer it should be. Okay, but that's not the matter. Sometimes the question is marked based upon the concepts, the depth of the concepts needed. Okay, the complexity involved, not the length of the question. So yeah, this is for our vectors. So we have successfully added it. Similarly, subtraction works the same way. Okay, now let's talk about multiplication and division. Okay, what is allowed with vectors, okay, and what's not allowed with vectors. Because in terms of division, first of all, let me talk about division. You can't divide number by a vector. Okay, there can't be a vector in the denominator, never. You can divide vector with a scalar, for example quantity 3, 4, 5, 6, a number or a scalar quantity. You can divide a vector by a scalar quantity, but you cannot divide anything, scalar or vector, by a vector. Okay, vector cannot be appeared in the denominator mathematically or the way we define it. Okay, so this is not permissible act. So yeah, division, there is a simple rule that we can only divide a scalar by a vector. For example, if we have 1 by 3 into r vector, okay, this is simple, that is it, nothing else is allowed. Now let's talk about the multiplication of vectors, how their multiplication look like, because we almost all of us know about scalar products, vector products, scalar triple products, vector triple products. They are really important, so let's now talk about them. Let's talk about vector multiplication, that how vectors are multiplied with each other. Okay, and what is the rule to follow. As I told earlier, the things that we discussed before are as important as knowing about scalar and vector product, because let me talk about some other physical quantity, which is torque, and we know that the torque is given by the vector product of position vector and momentum vector. Okay, so here you can see that even vector multiplication is involved in physics, in description of some physical quantities. So later on you will see that we'll have these operation applied on del operator as well. Okay, so you will see their application multiple times, how the scalar product, vector products, the triple product, or something like that is involved. So we should know about these things as well. And let's have a basic introduction to these vector products and these vector multiplications, and there are four kinds of vector products. The first one is scalar product, which is a double product. We have two vectors. The scalar product and vector products, these two are the basics one, and they are product of two vectors. Okay, so if we talk about scalar product, the first one I wrote is scalar product. This is a double product. By double we mean we have two vectors whose product is calculated by this rule. And let's say we have two vectors, A vector and B vector, and we describe the scalar product of two vectors by having a dot in between those two vectors which are being multiplied by this rule. Okay, so A vector dot B vector, we describe it like that, and that is equals to, in principle, that is equals to A, which is the magnitude of A vector, multiplied by B, which is the magnitude of B vector, multiplied by cos of theta. Theta is the angle between A and B. For example, we have this vector A geometrically, and let's say we have this vector B. Okay, so this angle, this is the angle between A and B. Okay, this is the angle between A and B. So A dot B is equals to the magnitude. We can also represent magnitude by this vector notation and these mods. Okay, it shows the magnitude of A vector multiplied. These are scalar quantities, that is why we have not shown any dot or arrow sign over it or something like that. Okay, we don't need it. So into cos of theta. Okay, this is the scalar product. And why it is called as scalar product? Because it results a scalar quantity. We had two vector quantities here, A and B. These are the vector quantities, and the result you will get will be a scalar quantity. So that is why it is known as scalar product, because it results a scalar quantity. It gives you a scalar quantity while the input quantities were vector quantities. Okay, next we have vector product. Okay, as the name suggests, since this one was scalar product, so on multiplication a scalar quantity resulted. Okay, and besides that, another thing that is important to note is that there are two vectors involved. Okay, there are two vectors involved, and the result that we got is a scalar quantity. It means it is a scalar product. Now vector product is the multiplication of two vectors that results into a vector quantity, so we call it as a vector product. Okay, and it is denoted by cross sign between two vectors which are being multiplied by this rule. So we have vector A cross sign B. This is the notation for the vector product between A and B vector. Okay, and that is equals to, by rule, A, which is the magnitude of vector A, multiplied by B. These are scalar quantities, that is why nothing matters. Okay, you can deal them with ease. Okay, they don't need any protocol, while vectors need protocol, and there are specific things that we have to keep in mind before writing them. So AB sine of theta, theta is the angle between A and B, multiplied by n hat, which is the vector showing the direction of the resultant vector, and this vector is perpendicular to both A and B. Okay, it is perpendicular to A as well as B. Okay, so the vector product results into a third vector. Let's say it is a C vector. Okay, it results into a C vector whose magnitude is given by AB sine theta. It's the magnitude of that vector, and its direction is given by n hat, which is perpendicular to both A and B. Okay, so this is how the vector product works, and we normally call vector product as cross product because of the symbol that is used to represent it, and we call scalar product as dot product because of the dot symbol that is used to represent it. So it's dot product as well. Okay, there are two names that are given to them: scalar product or dot product, vector product or cross product. So these are most frequent vector multiplications that are frequently found in physics and mathematics. Okay, while scalar triple product and vector triple products are not that much common, but they are they appear in some of the cases, so we should know about them. It's not the case like we can skip them. No, we should know about them, that how they are named and how they are represented and how to deal with them. Okay, we should know about it. So yeah, now let's talk about the triple products, which are scalar triple product and vector triple product. Just as we had scalar double product, but we don't mention it because it's the basic one. We start with 2 because there are at least 2 quantities whose product to be calculated. If there is only one quantity, then the product doesn't make sense now. That's why we call the basic ones as it is. We don't need to mention the double word here, but for the triple ones we have to mention it. So it's scalar triple product when we have 3 vectors involved, and the result we get is a scalar quantity in scalar triple product, while in vector triple product we have 3 vectors, and the result that you will get after multiplying those 3 vectors is a vector quantity. So that's how they are named. In scalar triple product we have 3 vectors, right? And their notation is, for example, we have 3 vectors A, B and C. Alright, we have 3 vectors here, and if we want to write the scalar triple product, then how we'll write it? It's like the first vector, which is, let's say, A, with arrow over it, dot. Since it's a scalar product, it will involve a dot. Dot with what? With another vector, this. Okay, you can't put dot here. There is a reason behind it. For example, if you put a dot here, what happens is that B dot C, okay, B dot C, B vector dot C vector, this results into a scalar quantity. Okay, and here it is a vector operator which is dot, and it is only applicable between 2 vectors. There should be 2 vectors in between which you are applying that scalar or vector product. So there should be a vector right here, and for that purpose dot is not allowed here. There has to be one cross product, okay, so that B cross C results into a vector quantity. Okay, and this vector has a dot product then with A vector, and this whole thing will result into a scalar quantity. As you can see, what happens is you first calculate B cross C. Okay, this B cross C gives you a gives you a vector quantity. The order of operation matters here. Okay, you first have to find out B cross C. You can't find out A dot B first. Okay, for the same reason of that if you first calculate A dot B, then you will get a scalar quantity, and you can't have a scalar quantity to have a cross product with a vector quantity. Okay, this is not applicable, this is not permissible. So that is why you'll first find out B cross C, that gives you a vector quantity. Okay, let's say it gives you a D quantity, and you'll find out the dot product with D quantity then. Okay, and since it's a dot product at the end, and dot product has that property that it turns the vectors into a scalar quantity. That is why the result is a scalar quantity. So if you find it difficult to find out the order of multiplication, that whether to do this one or the other one, So use brackets first. Okay, that's the easiest thing you can do, because brackets are solved first and then the rest is solved. Besides that, you can use that rule, that what results what. Okay, as I told you logically, that if you find out a dot b first, then what happens, it's a scalar quantity, and you can't have scalar quantity multiplied with a vector quantity. Okay, to have a cross product with a vector quantity, you can multiply a scalar quantity with a vector, that's permissible, but to have a cross product, that operator in between them, that's not a permissible way to write them. Okay, to have an operator, that's a different thing. So that is how the triple product works, triple scalar product works. It's like a dot b cross c. Okay, you can change the order of writing them in cyclic order. For example, it's a, b and c. You can interchange their positions, but how? It's like you write a first, then b, as you can see, first a, then b, then c. Position of a, position of dot and cross remains the same, but you can change a, b and c, because sometimes you know the value of a dot b cross c and you want to find out the value of some other, you know, permutation of these three vectors. So it becomes easy if you know this rule. So if you write a, then b, then c, then a, that is how this rule will work. So with a is first, then b, then it is followed by c, and then a. Now if we want to start with b, what happens is first is b. If you want to write b first, then dot will, the position of dot and cross remain the same, that is the rule. Okay, b, then comes c, so you will write c here, then position of cross, then a. Both of them are equal to each other. Okay, both of them will result the same quantity. That is what I trying to say. That's the significance of knowing that rule. But if I want to start with c, what happens? We'll use that same rule, c, then a comes, cross, then we have b. So that is how we can write them and remember them. Okay, this is the scalar triple product, and these are scalar quantities, and these three are equal to each other, and you can use this, rule to, you know, interchange the position of vectors. This property is used, you know, onwards in solving the problem to make some, you know, to derive some required forms. Okay, now besides that, we also know one other uh, relation about dot product, that dot products are commutative. It means if we have a dot b, then you can write it as b dot a as well. You can change the position of vectors around dot only. Okay, not around cross but around dot. For example, if I had this form a dot b cross c, that what can happen is I can shift the position of b cross c and a between dot. It results it into a b cross c. We can write them first, then dot comes, then a. Okay, I have just changed the order of the vectors. Okay, so they both are equal to each other. Similarly, if I had this form b dot c cross a, then I can write it as c cross a first, since it's one of the vector, then dot b. We can change the order of the product. Now besides that, what happens if we change the position of vectors in cross product, which is vector product? So if I had a cross b, then it's the property that if we change the location of vectors, if I write b first and a next, then what happens is negative sign is there, so the direction is changed, Hence we say that the cross product is non-commutative. Is A cross B can be written as then minus B cross A. Okay, there is a appearance of negative sign, and so if I had A dot B cross C, and if I shift the position of C, then what happens is here is A remains the same. If I write C first, then B, then we have to have negative sign here. This negative sign comes in the start, so this is the final form. Okay, so this is what happens when we have shifting between the cross. Okay, in between the cross. So yes, this is all about scalar products. Okay, you can easily calculate them. All right, and what is the rule to calculate A dot B? This is another thing. I'll make a separate video where I'll show you people how to calculate scalar products and how to calculate vector products, because the length of this original video will become very, large, and I don't want it to be really lengthy, because you people will say that we can't see it's too lengthy. So that is why I'll make a separate video where I'll describe you people the method to calculate scalar products and vector products, the triple and the scalar products and vector products. So triple vector product, how it looks like. Let's see. Triple vector triple vector product, or vector triple product, what it was, it's vector triple product. Okay, so how it looks like, it's like 3 crosses. Okay, and the order matters again, and it's usually written this way with the brackets on to show the order. Okay, because how we are supposed to know the order, because there is no rule that if I calculate A cross B first, okay, then it gives a vector, and vector cross C, that's permissible. So we have to use the brackets in order to ensure that we are calculating what is intended. Okay, so the order matters and brackets matters as well. Now if I want to change the position of these vectors, then the same rule applies. Okay, if I want to write B first, then we'll have C cross A here. That would be equals to, if I have C first, then cross A cross B, then these are all equal to each other. Okay, if I shift the position of any of these vectors, let's say this is one of the triple scalar product, and I want to write it first and then this one, then B cross C with negative sign but cross A. This is how we need to write it. Okay, so yes, this is the vector triple product, and there is an easy rule to calculate it. This is like, if you have this thing, then it is equals to back cap. We have that back cap rule. Let me back BAC minus cap. Okay, I have to write cap here. This is not here. Okay, there is no option to eradicate, to rub it, that is why I have to. So back cap rule, where is the position of dot and cross? It's like there is bracket here, there's a bracket here, the first one is left, it's a dot in between them. Now let's write vectors on them. They're all vectors, and there's a dot between the second ones. Okay, this is a back cap rule. There is a simple notation. If it's in this form, then you can write it like that. So if the notations are different, you can simply use this general rule to write them accordingly. For example, if it is 3 4 and oh my god, I'm writing scalars in place of vectors, how dumb I am. So let's say this is 3I hat, this is 4j hat, this is 3k hat plus 4j hat as c vector b vector. You can simply first let them as equals to a, b and c, then use back cap rule. Okay, you can easily calculate them, and in a separate video we'll see how to calculate scalar products and vector products. Okay, what's the rule, determinants, and we'll be introduced to those concepts. I'll link that video in the description box if you want to see it. If you already know that how to calculate scalar products and vector products, that's perfect. And let me tell you that I enjoyed this lecture very well. I hope you people enjoyed it as well, and I'll see you in next video. Till then, take care, and in next video we'll be discussing about del operators. Okay, we'll discuss about them because now we know what are vectors, so we can jump into the operators now. Okay, so yeah,